Hello, I am Yesenia.
And I am Rachel, and we are both research engineers working on the project called MAProHand, which basically revolves around the development of a prosthetic hand for below elbow amputees. Today we are here without our masks just because we are 2 meters away from each other. So, in order to start off, what is a prosthesis?
A prosthetic device is crafted with the aim of replacing a specific missing body part to restore its function and appearance. We all know how important and useful our hands are to us, especially considering that we would not be able to perform most of our activities if it weren't for both of our hands. In fact, we live in a two-handed world where almost all daily activities require the use of both hands, where each hand helps the other to get the job done. For example, when tying a shoelace. So one can only start to imagine how difficult it becomes for an amputee to learn how to live with just one hand, and this is where prosthetic hands come in.
Throughout the years, there have been several prosthetic solutions and development of different prosthetic hands in order to help these people, these amputees, to still carry on with their daily lives as usual, while still trying to satisfy their different amputee requirements. Because if the amputees are not satisfied with specific requirements that they have, they tend to not use their prosthetic hand anymore. For example, some people prefer that their prosthetic hand has a human-like appearance, and they have other requirements such as comfort, function, ease of control, sensory feedback, and many others. However, end-user satisfaction is not very easy to obtain, and the currently available prosthetics are known to achieve the balance between 3 very important attributes, which are simplicity, dexterity, and usability, while also still satisfying the previously mentioned amputee requirements.
But what do simplicity, dexterity, and usability stand for? Simplicity refers to a straightforward design, which in turn is more reliable and less expensive. For example, prosthetic hands, which focus solely on their aesthetics rather than function, are considered to be simple. Meanwhile, dexterity refers to the ability of the hand, for example, to be able to manipulate the pen like this. Finally, usability refers to a device which has certain qualities, making it easier for the amputee to use. For example, a prosthetic hand which is controlled through a mobile phone is not that particularly useful in our day-to-day activities. And this is where the MAProHand project comes in. The main goal of this project is to design an innovative prosthetic hands which essentially takes care of these 3 features.
In order to design a prosthetic hand which replicates an actual human hand while still satisfying all the different features requires the input of several different fields, namely engineering fields such as mechanical, robotics, electrical, and biomedical, as well in conjunction with the medical field, which leads us to start investigating the different elements that we need to tackle to design a successful prosthetic hand. So let's get to it, shall we?
To start identifying the main mechanical aspects required to construct a prosthetic hand, we need to start from the understanding that the human hand has a very complex architecture. In fact, did you know that the hand is made up of 27 bones linked together through different joints, nerves, and muscles? The different joints in our hand is what allows us to open and close our hand, to point fingers, and perform other grasps which may be useful for our day-to-day activities, such as when writing or drinking. This large number of joints, in fact, is usually a problem when it comes to designing a prosthetic hand due to the size and weight constraints. The hand allows us to interact and manipulate different objects in our surroundings by using different grasps. These grasps can be classified into 9 main grasps, which are cylindrical grasp, oblique palmar grasp, hook grasp, lumbrical grasp, intermediate power precision grasp, pinch grasp, lateral pinch grasp, special pinch, and non-prehensile grasp. An experiment you can try at home is to hold a number of different objects of different shapes, size, and weights, and observe which one of these grasps you are using to hold that object. An observation that you may make when doing this experiment is that a number of objects can be grasped with different grasps. For example, the mug can be grasped from the top using pinch, or from the side using the same type of grasp, or using a cylindrical grasp. It can also be grasped from the handle using an oblique grasp. This means that if the amputee is able to use the prosthetic hand to perform a limited number of grasps, he will still be able to perform a large number of day-to-day activities. Now that we have determined which grasps are most useful for the amputee, can we increase the simplicity of the prosthetic hand but maintain the same level of dexterity? In other words, can we achieve these grasps using less joints, thus using less motors which add weight, cost, and size to the prosthetic hand? You can test this at home by trying to constrain different joints of your hand, such as constraining the PIP and the distal joint together, which are the joints over here. Or you can constrain the motion of the index and the middle finger together. Then try to grasp the objects that you used in your previous experiment and comment on your ability to be able to grasp these objects. By using these ideas, we can start generating different concepts for the prosthetic hand and initiate their development in more detail. We also need to start thinking about how will the different joints be actuated and what manufacturing processes will be used and the materials that will be used to build the design. Once a prototype of the prosthetic hand is built, we can then evaluate its performance in terms of the amputee's requirements.
When we started thinking about the control aspect of the prosthetic hand, we asked ourselves, how can we make it easier for the amputee to use his new prosthetic hand without actually having to relearn how to use his hand again? And we concluded that we can actually do this by exploiting the sense of intuition that we all have as human beings whenever we proceed to do any kind of hand movement. We can all agree that most of the time we do not actually think about which muscles we want to activate whenever we want to grasp something. So even while I'm talking to you right now, while I'm doing specific gestures, I'm not actually thinking about what kind of signal my brain is going to send to my muscles, but rather my brain just does it subconsciously for me. So this is where the sense of intuition comes from. But how can we exploit the same sense of intuition for the amputees to start controlling their new prosthetic hand? So let's start off from our nervous system. Our body's nervous system is one responsible for activating specific body parts as a response to some event that has occurred. The central nervous system is the main controlling center, deciding which actions should be performed, when and how. In response to a signal from the brain, changes within the muscle particles create an electrical signal called an action potential, enabling the muscle to contract. This is where the concept of surface electromyography comes in. So let's make it simple for everyone and just call it EMG. EMG electrodes are able to record the combination of these different action potentials which are being generated in the muscles used for any hand movement. In brief, we are recording the motor unit's electrical activity, which increases and decreases according to the muscle activity. In fact, the bigger the muscle contraction, the larger the recorded signals are. So, as we can see from the signals on this band, I have 8 different electrodes placed over here, and we can see 8 different simultaneous signals corresponding to the different hand muscles that the electrodes are placed on. So while I am resting, the signals are quite inexistent, they are at rest, but once I start actually doing some kind of movement with my fingers, we can actually see different amplitudes on the screen there. So this is what these signals will actually, that are all the time firing up according to a response from these muscles, will help us to then give the amputees to give their sense of intuition back at the end of the day. Therefore, for this project, we are actually looking for differences between the detailed EMG signals obtained during finger movement so that we can then deduce the amputee's required hand movement. This decision will then tell the prosthetic hand to start moving towards that direction accordingly. This is different from some other hand control systems which actually require the amputee to use a completely different gesture from the one the prosthetic hand will eventually do.
Which leads us to the question of how will we achieve this trade-off that we initially mentioned between simplicity, dexterity, and usability. With the use of EMG to control the hand, we are designing the overall system to be simpler for the amputee to use, provided that there are no large learning curves, in turn leading to an overall increase in the level of usability.
In the meantime, from a mechanical design point of view, the reduction in the total number of joints will make the system simpler. However, by intelligently choosing the number and types of grasp to be made available to the amputee, the level of dexterity shall be sufficient for the user, whilst in turn also leading to a usable system. Overall, this combined system is envisaged to be a satisfactory extension for any below-elbow amputee to easily use within their daily lives.
This project is a collaboration between the Department of Mechanical Engineering, Department of System and Control Engineering, and the Department of Artificial Intelligence within the University of Malta and an industrial partner, Orthopedic Center Malta. The project is funded under the MCST Fusion Research and Innovation Program.
We hope that you found this interesting and you will keep on following us throughout this research journey. Bye.